Hello. Yes. In example 4, we solve this this problem by considering three cases. There is no such a rule requires us to consider three cases always. It depends on what kind of this interval is. If an interval is an open interval, such as a finite open interval, then every point of this interval is an interior point. So we need only consider one case, because the end points are not in this set. Okay. If we consider a closed array, some function, whether it is continuous on some closed array, we need to consider two cases. One is a point which is interior to this closed array, case 1. And case 2 is only one, because this set only one endpoint. So we need to consider, for example, here, left endpoint. Then that's all. If array is an open array, it is an open set. So we again only need to consider the case 1, because all points of this set are interior to this set. Okay. Okay, let's draw a picture, which is the graph of this function. Sketch the graph of this function. We have a square root part here. So we first consider this function. This expression is equivalent to if we square it. But if we take square root, the right hand side back to the original form. But the left hand side, y squared then square root is the absolute value of y. So these are not equivalent. These two expressions are not equivalent. The lower one is a necessary condition of the upper one. The upper one is a sufficient condition of the lower one. In order to then these two statements are equivalent, we put additional relation here. Okay. Because according to this one, y is the value of a square root. Y definitely is not negative. If we take square root, then the left-hand side of this equation becomes the absolute of y. Absolute value of y, when y is not negative, it is y. Okay. Let's rewrite the first equation in more familiar form. This is exactly the equation of a unit circle. And the y is greater than or equals 0 means the upper half plane. Upper half plane. This is y equals 0. This is y equals, y is greater than 0. This part is y is less than 0. So y is greater than or equal to 0 stands for the upper half plane. And this one is the equation of the unit circle. Intersection, we obtain so this function whose graph is a upper hemicircle. Upper hemicircle. If we replace this one by its negative, then we replace this relation by y is less than or equal to 0. Less than or equal to 0. We obtain the lower hemicircle. So the graph of this function minus means reflect this about the x-axis to obtain a lower hemicircle. And the 1 means shift 1 unit above. So finally, what we obtain the graph of this function is reflect, shift. So this curve obviously continues on this closed interval, -1 to 1. Okay. From here to here, the coordinates of this point is -1, 1. The coordinates of this point is 1 and 1. And the curve of this function is yes, lower semicircle at this position. Okay? Example 5. We have solved this problem once when we studied the limits or used limit laws to solve this problem. But now we have another explanation. Since this is a rational function, if this point is in the domain of this function, we can, because then this function is continuous here. So, okay, -2, this is 11, non-zero. But the continuity of this rational function, the value of this one will be by letting x be as -2. -8. minus 14, minus 15. And the denominator is 11. Oh, wait a minute, 2x squared, huh? Squared, minus 2, minus 8, this is 8, cancel. So we have a minus sign, and this is 11. So this time the reason is like continuity of this function. Rational function is continuous on its domain. Okay. Before we use limit laws to solve this one, but now we use the continuity. We already know this function, rational function is continuous on its domain, and minus 2 is in its domain. So we find this by evading. And this function at the value of this function is minus 2. In this example, on what intervals in each function is each function continuous? Okay. Continuous on an interval. Find the interval. This function is a polynomial function. It is continuous everywhere. So, in terms of intervals, the reason is f is a polynomial function. Of course, you can replace this by RIs very well. Also, allow same. Okay, here, the domain of the function g is the set of all real numbers such that x squared minus 1 is not equal to 0. It's not 0. Then if a product of two numbers is 0, then at least one of them is 0. So maybe this one is 0 or this one is 0. X equals minus 1 or x equals 1. Therefore, the domain of G is the set of all real numbers except minus 1 and 1. Okay, for a real number line with -1 and 1 are deleted, we have 3 open intervals. Of course, continuous on this is a maximal intervals. In fact, any subintervals of these 3 intervals are also available, no matter closed or open or half open. Here I just write down the maximal one. Okay. Maximal one means you cannot extend further because proper set of this one must contain -1. OK， 好，在这里呢，我写的答案是指极大的这些是它连续的区间，极大就是说再大一点就会包含一些不连续的点在里面。这里也是一样，要区间要比这个大一点，势必会包含负音，所以就不再是在那个区间上连续。那既然是写极大，任何这些区间的子区间，不管是开或闭或半开，也通通合适。所以为了方便起见呢，我只写出极大的极大的区间就是。So for convenience sake, we to find open interval maybe automatically means to find the maximal intervals such that f is contains on that interval. Okay, or intervals. For part C, this function is a sum of 3 functions. The first one is square root function. The domain of this function is array from the origin to the right direction. And for this function, this is a rational function whose domain is the real number line except x equals 1. So in order to hx is defined, x cannot be 1. So 1 should be deleted, should be throw. Okay, throw. For this one, this is also a rational function, but the denominator number is 0, at least 1. So in order to hx is defined, x must be positive and distinct to 1. Okay, once this function, the value h of x is defined, it will be continuous there, especially at 0. This one is continuous from the right, and this one is continuous from both sides. In summary, the function h is continuous on this half-open interval 0, 1 and this open ring, the infinite and infinite open set. Very well. Example 7. Find this limit. Okay, this is a quotient of two functions involving constant and trigonometric, sine and cosine. So this function is continuous on its domain. At pi, says cosine pi, where is pi? We know the arc length, the length of the circumference of this circle is 2 pi. So pi means from here to here. This is the position pi. And the coordinates of this point are cosine pi and sine pi, which is -1 and 0. So cosine pi is -1. Since this function is continuous at pi, sine pi is 0. And the cosine pi is -1. 0 over 1 is 0. Okay. Example 8, where are the following functions continuous? Okay, the first function, this is a continuous function of a continuous function. Continuous. The domain of x squared is the entire real line, real number line. They are all defined, and the sign is also defined everywhere. So the composition of these two functions is also continuous on R. Where are the following functions continuous? So you can answer this problem in two ways. One, at some point. Two, on some interval. Yes, continuous everywhere. Or continuous on R. Okay. On R. Or continuous everywhere means locally, at every point, everywhere, or on R. Okay, again, this function is obtained by a constant function, identity function, after finally many steps of addition, multiplication, subtraction, and or powers or square root. This is a algebraic function. Okay, algebraic function. If a function not of this kind, we call it transcendental function. Just a terminology. 就这个函数是经由常数函数跟恒等函数经过有限次的加减乘除，以及方根所构成的，这样的函数称为代数函数。那不是代数函数的函数称为超越函数。So we have this terminologies: algebraic function and a transcendental function. Algebraic function almost can be obtained its value by direct substitution. So this function is continuous everywhere in its domain. And at what position make the denominator 0? Take square root. Square root of 17 is exactly this one. Because the square root find the non-negative value. Okay. Now, if we consider the real number line and with minus 3 and the 3 are deleted, are removed, deleted, then we obtain the 3. Of 4 open intervals. 2 of them are finite open intervals, and 2 of them are infinite open intervals. Okay. We may describe this one by f is continuous at every real number or everywhere. Except at the numbers 3 and the minus 3, except with some exception. Okay. So we may describe the answer in terms of interval also at some points, some numbers. Oh, sorry. It's 0 it's in its domain. So only 3 open intervals. One is bounded. Another 2 is unbounded. Or finite or infinite event. Bounded or unbounded.